Hello everyone, myself Ishika from BSc Chemistry Honours Final Year. Today I'll speak about topic Raman Spectroscopy. It is a special type of spectroscopy which deals not with the absorption of electromagnetic radiation but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with monochromatic light of a definite frequency, a small fraction of the light is scattered. Rayleigh found that if the scattered light is observed at right angle or to the direction of the incident light, the scattered light is found to have the same frequency as that of the incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance is irradiated with monochromatic light of a definite frequency, the light scattered at right angles to the incident light contain lines not only of the incident frequency but also of lower frequency and sometimes of higher frequency as well. The lines with lower frequency are called stroke lines, whereas lines with higher frequency are called anti-stroke lines. Raman further observed that the difference between the frequency of the incident light to that and that of a particular scatter line was constant depending upon the nature of the substance being irradiated and was completely independent of the frequency of the incident light. If mu I is the frequency of the incident light and mu s that of the particular scattered light, the difference delta mu is equals to mu I minus mu s is called Raman frequency or Raman shift. Thus, the Raman frequencies observed for a particular substance are characteristic of the substance. The various observations thus made by Raman constituent what is called Raman spectroscopy, and the spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be expressed as shown in figure. Explanation for observing Rayleigh line and Raman lines. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains Rayleigh scattering or Rayleigh line. However, if the collision is inelastic, still the law of conservation of energy will hold good, that is total energy before collision and after collision must remain the same. Thus some energy may be transferred from incident photon to the molecule so that the scattered photon has lower energy and hence lower frequency than that of the incident photon. This explains the occurrence of stroke lines. Alternatively, some energy may be transferred from incident photon to the molecule so that the scattered photon has higher energy and hence higher frequency than that of the incident light. This explains the occurrence of anti-stroke lines. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to the original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. In many, it may return to a level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of stroke lines. Thus, a part of the energy of the incident photon remains absorbed by the molecule. Alternatively, the excited molecule may return to the lower level than the original level, thus more energy is emitted than absorbed. This explains the occurrence of anti-stroke lines. In this case, the molecule has less energy than before. Levels Polarizability of molecule and Raman spectrum. The Raman effect arises on account of polarization of the scattering molecule that is caused by electric vector of the electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field E and nature of the molecule, where we write mu equals to alpha E, where the quantity alpha depends upon the nature of the molecule and is called polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of atom or spherically symmetrical molecules such as CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules or non-spherical molecules, the polarizability depends upon the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more than the electric field is applied parallel to the bond, that when it is applied perpendicular to it, and we write alpha parallel is greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Types of molecules showing rotational Raman spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectrum is that the polarizability of the molecule must be anisotropic, that is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of electric field. Hence, all diatomic molecules, linear molecules, and non spherical molecules give Raman spectra, that is, they are rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6 do not give rotational Raman spectrum, that is, they are rotationally Raman inactive. In fact, this is one of the reasons for importance of rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former only requires that polarizability of the molecule must change during vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is the sum of two parts: equilibrium polarizability, that is the polarizability when the atoms of the molecules are in their equilibrium position, sum of the polarizability of the molecule due to the various rotational and vibrational motions, each term depending upon the frequency of rotation or vibration, where alpha n is the polarizability molecule associated with the nth rotational or vibrational mode, and Rn is the maximum displacement of the atom involved. Quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are delta J equals to 0 or plus minus 2. The selection rule delta J equals to 0 correspond to Rayleigh scattering, whereas selection rule plus minus 2 gives rise to Raman lines as explained below. We know that the energy of a rotational level in terms of a wave number with quantum number J is given by mu bar equals to bj into j plus 1, where when a transition takes place from lower rotational level with quantum number j to a higher rotational level with quantum number j dash, the energy absorbed in terms of wave number will be given by the following formula. Here mu I dash bar represents wave number of Rayleigh line, plus sign gives lines with higher wave called anti-stroke lines, and minus sign gives line with lower wave number called stroke lines. From equation 5 it may be seen that for G equals to 0, mu bar equals to mu bar I equals to plus minus 6b, that is first stroke line, and anti-stroke line will be at the separation of 6b from the Rayleigh line. Intensities of line of the pure rotational Raman spectra. As explained earlier, the intensities of lines depend upon the population of initial level from where the molecule are excited or de-excited to the final level. Since the population of rotational energy levels as shown, therefore the intensities of the stroke and anti-stroke lines vary in a similar manner. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation between the lines, the value of B can be obtained, from which the moment of inertia and the bond length of the diatomic molecule can be calculated as explained earlier. Quantum theory of rotational vibrational Raman spectra of diatomic molecules. For large molecules, lines obtained due to rotational transition are so weak that they are beyond resolution. Hence, we have pure vibrational Raman spectra for which the selection rules are same as pure vibrational spectra. However, in case of diatomic gaseous molecules, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecule gives rotational vibrational Raman spectra, which can be explained as follows. The selection rule for the transitions are delta V equals to plus minus 1, delta G equals to 0 or plus minus 2. However, at room temperature, as most of the molecules are in the lowest vibrational level, therefore, the significant vibrational transition is from V equals to 0 to V equals to 1, called fundamental vibration transition. Restricting ourselves to this vibrational transition only, the result obtained is as follows. Representing the value for QSO branches wave number of exciting radiation by mu I, the wave number of the stroke lines will be as follows. We have considered the case for delta V equals to plus 1, which represents stroke line. The anti-stroke are those for which delta V equals to minus 1. They are usually weak because very weak molecules are in the vibrational state initially. The rotational transitions accompanying the vibrational transition from V equals to 0 to V equals to 1, a rotation vibration Raman spectrum obtained may be as follows. Advantages of Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. Since Raman frequency are independent of the frequency of incident radiation, hence suitably adjusting the frequency of the incident radiation, Raman spectra can be obtained in the visible spectrum range from where they can be easily observed rather than the more difficult infrared range. Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Raman spectra can be obtained not only for gases but even for liquids and solids, whereas infrared spectra or liquids and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of a compound, large number of compound has been determined by Raman spectroscopy. However, infrared method still continues to remain popular. Thank you.